Welcome students once again into my class of topology. Previous video I had to stop due to some interference in the room, and now I am continuing from there onwards. The next theorem which we are going to prove is that let C be a collection of subsets of X, then there exists a filter F containing this collection C if and only if C has FIP, that means finite intersection property. And if and only if means the converse of the theorem is also true, that means if C has FIP, then there always exists a filter F containing C. So we start with let this family C has FIP, that means finite intersection property, that means intersection of every finite collection of members of C is non-empty. This is given to us. Let B be the set formed by finite intersections of members of C. So this collection B contains the set B, where B is finite intersection of members of C. Intersection of members of C. And using this collection B, we will create another collection F. So let F be the collection of the subsets F of X such that F contains B for some B in the family B. And now we will show that this is the required filter F which contains C. So what we have to prove that? What we have to prove for that? The three properties of filter. That means it does not contain phi. If F is a member of it, then every superset of F is also in the family F. And if two members F and H are there in the family F, then their intersection will also be a part of this family. So let us start one by one. 1. F contains F. Let F be a member of this family. Then by definition, F contains B for some B belonging to B. And what this B is finite intersection of members of C. So intersection of C where C belongs to this collection, and this is a finite intersection as we have defined here. And we are given that C has FIP. That means this intersection cannot be empty. This is non-empty. So B is non-empty. And since B is non-empty, its superset cannot be empty. So F is non-empty. So this means F is non-empty. That means if for any F belonging to F, F is non-empty, this means phi does not belong to this family. So the first property is proved. Now we move on to the second. In the second, we will take one set F belonging to this family. Let F belongs to F, and let H be a superset of F. Now F belongs to F. By the definition, F contains some B for some B in the collection B. Now F contains B and H contains F. By using transitivity, we can say that H contains B for some B belonging to B. And if H contains some B, by the definition of F, H belongs to the collection F. We have taken F belonging to this family and H superset of F, then H also belongs to this family. That means the second part is also proved. And finally, we will prove the third property for this F to be a filter on the set X. Thirdly, let F, H be two members of this family. Then there exists some B and C in the family B such that B is contained in F and C is contained in H. That means B intersection C is contained in F intersection H. Now look at what B and C are. B and C are the members of B, and the members of B are finite intersection of members of C. So that means B is a finite intersection of members of C. C is also a finite intersection of members of C. So their intersection is also a finite intersection of members of C. So it belongs to B. And now B intersection C is a member of B, and F intersection H contains it. And whatever the set contains a member of B is a member of F. So F intersection H belongs to F. The third property is also satisfied. That means it is a filter. And now we are also to prove that this filter F contains C. And this is very clear. B contains finite intersection of members of C. So if some C is there in C, C will also be there in the B by taking single intersection C with itself. Now C belongs to B. And if C is a member of B, then a set containing C belongs to F, and C also contains C itself. So C belongs to F. So this means C belongs to F. You have taken C from the set C, and now C comes in the set F. That means the collection C is contained in the collection F. So F is a filter that contains the collection C. One way the proof is clear, and now we will move on to the converse part. Conversely, we will suppose that for every such set C, there exists a filter F containing C. So C is a collection and F is a filter. F is a filter such that F contains C. We have to show that C has finite intersection property. Let C1, C2, Cn be a finite number of members of C. What we have to show that their intersection is non-empty. Since they are the members of C and C is contained in F, so they are also contained in F. Now this C1, C2, Cn are the members of F, and F is a filter. By the third property, we know that the finite intersection of members of a filter is also a member of the filter. So this means intersection of these Ci's, I vary from 1 to n, is a member of F. And F is a filter. We know that phi does not belong to F, so it cannot be phi. So this means this intersection Ci, I vary from 1 to n, is non-empty. And that is what we wanted to show. We have taken a finite number of members of C and we have shown that their intersection is non-empty, and this shows that the collection C has FIP, which we wanted to show. So this was the first theorem of this video. Now we will move on to another very important theorem based on filters. Let us see what the theorem is and how to prove it. So first of all, write the statement of the theorem. Let F1 be a filter on a non-empty set X, and let A be a subset of X, then there exists a filter F2 finer than the filter F1 such that the set A belongs to F2 if and only if A intersection F is non-empty for every F belonging to the filter F1. This is the statement of the theorem. So F1 filter is given to us on a non-empty set X. A is a subset of X. What we have to show that if there is a filter F2 finer than F such that A belongs to F2, then A intersection F is non-empty for every F belonging to F1, and the converse is also true because you are having here if and only if. So let us move on to the proof of this theorem. So firstly, I'll take let A intersection F be non-empty for every F belonging to the filter F1. So this condition I have taken, and what I want to have, I want to prove that there is a filter F2 finer than the filter F1, finer than the filter F1 such that A belongs to F2. Let us have a collection script A, the different notation I am using for A, such that it contains A intersection F, where F is a member of F1. So this collection I have taken as the collection A. Firstly, we will show that this collection A has FIP. Claim A has FIP, and this is very easy. We take finite number of members of A and we will show that their intersection is non-empty. Let A intersection F1, A intersection F2, and so on, A intersection Fn be finite number of members of the collection A. Now we have to show that their intersection is non-empty. Their intersection A intersection F1, intersection A intersection F2, intersection and so on, intersection A intersection Fn can be written as A intersection F1 intersection F2 intersection F3 and so on, intersection Fn. Now this F1, F2, F3, Fn, they are all members of the filter F1. So their intersection must also be a member of the filter F1. So I'll name this set as F. So it is A intersection F, where what is F? F is a member of F1. And we know that if F is a member of F1, then A intersection F is not phi. This is given to us. We have taken that A intersection F is not phi if F belongs to F1. So this is non-empty. We have taken a finite number of members of this collection A and we have shown that their intersection is non-empty. By the previous theorem, A has FIP. So therefore, by the previous theorem, there exists a filter F2. I am removing this proof from here because this part we have proved that A has FIP. By the previous theorem, there exists a filter F2 such that A is contained in F2. Now, we are to show that this filter F2 is finer than F1. What to prove? To prove that F2 is finer than F1. So we'll take one member from F1 and we'll show that it is also there in F2. Let F belongs to F1. Let F belongs to F1 and we are to show that this F1 belongs to F2. Now A belongs to F1, F belongs to F1, and for F belonging to F1, A intersection F belongs to A. So A intersection F belongs to this collection A. And A is a subset of F2. So this means A intersection F belongs to F2. Now F2 is a filter and A intersection F has a superset F, and we know that in a filter, if a set is there, then every superset of that set also belongs to the filter. So this F must be there in F2. From where we have taken this F? We have taken F from F1 and now we have shown that F is in F2 and this proves that F1 is a subset of F2. So first part we have shown that if A intersection F is not phi for every F belonging to F1, then there exists a filter F2 containing F1 which is finer than containing F1 such that A is a subset of A belongs to F2. Now we are moving on to the converse part. For the converse, let F belongs to F1, and since F1 is contained in F2, it is given to us now. So F belongs to F2. Also A belongs to F2. F belongs to F2, A belongs to F2, F2 is a filter, so A intersection F belongs to F2. A intersection F belongs to F2 and F2 is a filter, so A intersection F is not phi for any F belonging to the set F1. Now I think this part remains to be proved in the previous part that A belongs to F2, and that is once again very easy. We have shown in the previous part that A intersection F belongs to F2. Also, A is a superset of A intersection F. Once again, A intersection F belongs to F2. F2 is a filter. A is a superset of A intersection F. So A belongs to F2. This part I think was remained unproved in the previous part, so I have proved it here. So here I am going to stop this video. In the next video we will see supremum, infimum concept and their theorems. Till then, thank you. Thank you once again.